I'm speaking as part of the group that Robert and Mike have kind of laid out some of the introductory kinds of clinical and data volumes introductions. So I will be basically trying to pack in 2 talks into this session. It turns out that one of our students, Madi, was not able to attend because of his visa issues. So I'm going to try really hard to get you all out before midnight. If anyone gets cranky, just raise their hand, and I'll try and stop. Yeah.
We will have to stop you within reason.
So we have a collaboration that I've described at previous SPAM conferences with UCSF, Kaiser Permanente Northern California, McGill, and Persian. One of our colleagues from UCSF was supposed to come, Marie, but she had some family issues in Belgium, and she decided that it would be best to stay with her family. So we would have had even more talks about from a neonatologist point of view. Madi on the top right there will figure prominently in the second part of my talk, but this is our main group. We have quite a diverse set of skills, from the engineering side to the OB side to the pediatric neurology side and neonatology, as well as some really strong IT support and project management with a public health perspective from Jennifer. It's a really comprehensive group. So the data that we have has been described by Rob, and this is a summary of it. I'll just highlight the definitions of healthy. We have the healthy with no blood gas, where we presume that they were healthy. Healthy that did have blood gas, but there was no evidence of acidosis according to this criteria for pH and base deficit. And then HIE, we're trying to focus on HIE due to perinatal events and not chronic HIE. So we start by saying there has to be evidence of acidosis with the caveats that have been mentioned earlier, plus some neurological signs early in life and later for seizures up to 24 hours. And any one of these 3 signs can put us in the HIE group. So first I'm going to talk about the 3-tier and 5-tier classification, which many of you are aware of, and the FIGO classification is very similar in many respects. Basically, it the 3-tier categorizes into green, yellow, and red, whereas the Para-Ikeda 5-tier has the from green, blue, yellow, orange, red spectrum, and you see how each cell in this matrix basically corresponds to different kinds of features with different severities, and recurrence of decelerations is considered as a stronger marker than a single event of deceleration. So we were able to implement these guidelines because we can push our data through patterns. Perigin patterns gives us the baseline decel contraction events. XL is in there as well, but we don't really need it too much for the guidelines because XLs are indicate healthy state. So we push this through either the 3 or the 5-tier models, and we come up with a history of 20-minute windows, advancing every 2 minutes, and we look back 3 hours to kind of accumulate the durations of colors in each color over that past 3 hours. And at some point we have to decide how to interpret these colors. So first of all, what do we see when we apply the 5-tier system to the HIE cases that had no C-section? What the highest duration, yellow or greater, in the last 6 hours looks like. We have what you kind of would expect. I'm showing the last 24 hours of data if it's available, although we do go back, as Rob said, as far as 72 hours. But this is ranked according to the amount of yellow plus in the last 6 hours, and we're able to basically see some correlation with the higher yellow and orange. Red doesn't figure very significantly as it's so rare. On the other side of the spectrum, the healthies look healthy, they look green. Both the healthies that had no blood gas and the healthies that had no acidosis with the blood gas. So all that looks fine, except when you go to the other side, the abnormals can also have almost no sign of severity at all. And so we're ranking with the least amount of duration of yellow and greater. And these would be our missed cases according to the classification scheme. And the same goes for the acidosis cases. Many of them just do not exhibit the features that these guidelines are looking for. And at the same time, many healthies do exhibit these strong duration severities. And just a reminder that I am ranking hundreds of thousands of these, so there are a few that float to the surface, but in both the even the no blood gas, the presumed healthies, but those that had no evidence of acidosis from the blood gas, they could have some non-reassuring patterns for sure. So when we look at the last 3 hours and just sum up the 3-tier, the NIH, we don't see the typical 80% level that is often quoted. By the way, the N's here are not cases, they are epochs, so they're wildly high, and maybe I should have changed that. The main message here is that from the healthy side on top, the healthier, and the more abnormal on the bottom, we do see more yellow in the abnormal versus the healthy cases. But, you know, there's still, it's not 80%, but the gray, by the way, means there was no valid signal. So if you bump these up a bit, you get maybe close to 70% yellow for the HIE and so forth. But the main message of the Jackson paper, that category 2 is just a big grab bag of low severity and high severity cases, remains true. So if we look at the yellow 3-tier and say, okay, what does the 5-tier say if the 3-tier said yellow? And this shows that indeed the 5-tier does stretch out the spectrum. So you have even green. I wasn't expecting this much green, but that shows that the 3 and the 5 tier do have some disparities in their categorization, and that's something that I'd like to look at more carefully. This plot is fresh out of the oven, and I can state that it's
It's probably true, by the way.
probably true, yeah. But so we do see slightly more yellow, orange, certainly more yellow in the more abnormal cases. But it's subtle, and when we look at it over time, what I have here is basically there's 3 points in time that I'm looking at the distributions: 12 hours, 6 hours, and a time of delivery, looking at the acidosis and HIE cases on the right, and the healthy cases on the left, with increasing severity. Basically, there is a story here that there's more yellow plus. These are all plus, right? More yellow or more orange or more red or more. Red is just so rare. It's not almost. I put it there just to illustrate how rare it is. But we do see some differences in the distributions of the orange in the abnormal cases versus the healthy cases. But still, the question: what do we do with this? Do we have to select a cutoff? What is that cutoff going to be? Well, in an earlier paper that Colm Elliott and Emily Hamilton and I wrote many years ago now, we chose some clinically reasonable thresholds, and I put them here: 150 minutes of blue in the last 3 hours, 120 minutes of yellow in the last 3 hours, 42 minutes of orange, and you see where these cuts are. They're cutting off in the orange, in the tail of the distributions, and for yellow, yes, we do get a lot of the abnormal with high levels of yellow at that threshold, but look at how many we miss, and we're going to get some false positives. Yep. So performance, if we keep the false positive rate in black here, that's the overall average of all these healthy metrics, we see something on the order of 40-50% detection. This is basically a tenfold, looking at 10 tranches of data to get an estimate of the variance. My takeaway from this is there's still a large question. Is this better than what the clinicians actually did in reality? Because yes, we're getting some early detections, but we're also getting significant numbers of false positives. So this is ongoing work. Okay, so my next half of the talk, which is going to only be 3 hours, is this idea of foundational models, which I've been scratching my head to get a sense of what this means. I think everyone and their cousin are developing foundational models, but somebody has actually put some thought into this on the computer science side. So the characteristics of a foundational model, basically, if you can have access to lots and lots of data, yes, that is a good starting point. But is it general? Could it be used for multiple purposes? Is it reusable in slightly different contexts? Can you scale it with the proper hardware and so forth? I would like to add to those, for the clinical context, these ideas of clinical relevance and inherently interpretable, because I think we can easily get into a black box situation if we don't put thought into that up front. So the idea is here we've chosen a pretext task of forecasting the next 2 minutes of FHR, which serves as a self-supervised pre-training objective. High quality forecasting should encourage learning a comprehensive CTG characterization and vice versa. And the idea that we're going to learn the coupling between uterine activity and FHR is built in to the latent representation that we learn. And hopefully this is going to help on the clinical side. And this is Madi's work. So the main idea is, as I said, to predict 2 minutes ahead. Why 2 minutes? It's because most decelerations can last, the mean or the mode is about 1 minute, and 2 minutes is well into the tail, so it seemed like a decent horizon. And then we bring transfer entropy into the mix by saying the key question from transfer entropy is how much additional predictive information does the UA give about future FHR that the past FHR could not give alone. And so this is the idea of getting a sense of the coupling. We have two mechanisms in the forecast. One is intrinsic to the FHR through autoregression, which you can get the baseline predicting from previous baseline, but you get a lot more information about decelerations if you know that you're in a contraction. So basically, we only used our healthy cases for training. We have lots of training, lots of healthy cases, and so few acidosis and HIE cases. But we can take advantage of that to characterize FHR. We don't use any acidosis or HIE cases in this pre-training stage. And basically, we are wondering if we'll see the changes between healthy and abnormal when we do inference or testing. This is basically the overall pipeline. The features are based on scattering transform, which decimates in the time domain and expands in the feature domain. We found that time domain dimensionality is really expensive for learning, but you can add many channels at fewer time steps, and that helps keep training cost within reasonable bounds. So we use a modified variational autoencoder with this. It's a special kind. It's a transfer entropy bottleneck. The idea is to have a compression of the information that includes the coupling between the UA and the FHR in that representation, which we hope to use for classification. Here, I'll just give a few examples. This is some examples of actual predicted FHR at each of these vertical lines. The predicted FHR is in red, and the standard deviation around that, the uncertainty, is in green. And you see that the D cells and especially the deep D cells, are very well predicted. Interestingly, the variability shows up as a standard deviation or an uncertainty within really tight bounds of the peak-to-peak range of the short-term variability. When the important thing is that when we applied this to the non-healthy cases, we didn't see any clear difference in the prediction fidelity. In fact, it got better for the acidosis and the HIE cases in terms of SNR. And that was kind of reassuring, that the fact that we had focused our pre-training on healthies and taken advantage, I mean, it's only 20,000 of 200,000. We could maybe scale up even more, but as it is, training takes 4 days or so, so you don't want to do that too many times. Finally, what was the fidelity of the predictions? We looked at the low frequency and the high frequency fidelity. The low frequency was as you might expect, very good from what you saw on the previous slide. It's the higher frequency, and the further away you get from into the forecast horizon, that it becomes basically there's predictable things and there's unpredictable things, and it's kind of a spectrum. You know, what's reassuring here is it's a graceful fall off. And then finally, we looked at the surrogate for transfer entropy, which is the Kullback-Leibach divergence, which is built into the standard variational autoencoder. And we see more transfer entropy, or the surrogate for transfer entropy, in the unhealthy cases compared to the healthy cases. But these are kind of worst case confidence bounds, over 10-fold the maximum and the minimum. So we're still trying to sort out if those overlaps are saying that we need to work harder for separation or not. Here's an example, a latent representation for 20 minutes. You see that something's happening in this deep D cell that's showing up in some of the dimensions. I skipped over the fact that the latent dimension is about 16 dimensions and 300 time steps, and we also can track the instantaneous KL or transfer entropy surrogate. So, last slide. We can successfully predict the short-term or short horizon forecast of the FHR, and we can do it with quite decent fidelity. Low frequency is very, very well predicted. High frequency falls off with time and into the prediction horizon. And the coupling surrogate is showing differences, preliminary differences at least, that we expect, that transfer entropy increased with more or abnormality. So the future work is to validate this surrogate transfer entropy against an analytical transfer entropy estimate to see how close we are to that original definition, and test this on simulated data sets with known, basically synthetic data sets, and then transfer back to our UP FHR training context. So this is a work in progress.
Thank you very much. Looking forward to the paper. Should I take this as no questions? I would allow, yeah, of course. A lot of us have a lot of questions. We will never allow me to chair again, number one. Second, we'll continue discussions after. But yeah, three of you, I mean, just be quick so that we allow three of you. And I will say, obviously, the panel, we will reduce the time for it. But given that I forced each one and single of you for that panel, now I ate half of your time. That's fine. Just let's be reasonably quick, and we'll change the format for next time.
I can go first. Phil, can you explain briefly again how the approach works in real time? So the method takes a segment of data and extract features. Is that what it does, and then predicts what happens in the next 2 minutes?
Yes, we take a 20-minute analysis window, and in that analysis window, we're repeatedly forecasting 2 minutes ahead. And we basically include the fidelity of the prediction in the loss function within that 20-minute window, and we do that for all of our data.
Right. Does it do it independently from hopping from segment to segment, or it also takes into consideration the previous history, not just the previous segment or the current segment?
We'd like to be able to include the previous segment, but for simplicity, we've had independent segment predictions.
Okay. And finally, quickly, the latent process is what is it? The latent process that you had like 12 or something.
16 dimensions. You know,
yes. What do they represent?
They represent the bottlenecked embedding that has the effects of the two parts of the VAE loss, the KL and the reconstruction. In this case, a forecasting reconstruction.
Yes. Okay. Thank you.
Yeah, very, very interesting talk, Phil. I saw in one of the panels it was showing a prediction of a deceleration. So it's essentially be able to predict that deceleration ahead of time. And I assume it's because it's using kind of the joint fetal heart rate and uterine contractions that then might be able to predict, preceding a deceleration. Have you looked at all to be able to predict like a prolonged deceleration versus just the normal variable deceleration?
Well, the slide that I showed tried to show a little bit of diversity, as much as you could have in 20 minutes, of shallower decels and medium-sized decel and a super deep one. And we were able to predict that range, at least in that epoch, and we've seen that kind of consistently from preliminary look. Yeah.
Very interesting. Thank you.
Last one.
Right, quick one. So you explained this key 2-minute prediction, which I didn't catch really. Why exactly 2 minutes? And did you experiment it near this interval? So if you could briefly elaborate.
We did not experiment with that. And as I mentioned, we chose 2 minutes because that's kind of the far end of a deceleration duration. Yeah, so we could cut that in half and see slightly different results, perhaps. But I don't think we'd want to go too much further than 2 minutes.
Let's talk about it in the boat. Thank you very much, everyone.